Hello and welcome, everyone. This is Active LiveStream 56.1. It's November 14th, 2023, and we're continuing our discussion series on these 4 papers by Alexander Ororbia et al. Welcome to the Active Inference Institute, everyone. We're a participatory online institute that is communicating, learning, and practicing applied active inference. This is a recorded and an archived and a published live stream, so please provide us feedback so we can improve our work. All backgrounds and perspectives are welcome, and we'll follow video etiquette for live streams. Head over to activeinference.org to learn more about projects and learning groups at the Institute. Well, today in 56.0, we're bringing out all of the 4 entrees, and we'll see where we go with these big topics and with Alex here to discuss. So we'll begin with intros and go from there. So I'm Daniel. I'm a researcher in California, and what I would like to explore in this stream, beyond the trails that were left in the .0, is to get the zoomed in. What is the space of these micro motifs? And then to compose those zooming ins into the bigger picture. What do cognitive architectures look like in 2023? How is that different in theory and in practice than 1983? And then where is this all heading in terms of how we can do useful and important research? Blue?
Cool, thanks. Yeah, I'm interested in the 2043 cognitive architecture also, and maybe exploring the space of human cognitive architecture, but also like non-human cognitive architecture and what that looks like and where maybe that might take us. Yeah, that's good. Alex?
All right. I'm Alex Ororbia, and I am the director of the Neural Adaptive Computing Laboratory and a computer science assistant faculty professor here at RIT in computer science. I'm also affiliate professor in psychology, soon to be affiliate professor in cognitive science, and affiliate faculty in computational neuroscience. Kind of a mouthful of different involvements, but I do a lot. I've known about the Active Inference Institute before. Some of my students are fans of the channel already, so it's very exciting to be here to talk to you guys. And I think that you have some really good questions, and I think this set of papers that you picked is a nice little pathway through some of the thinking that I've done over the years. What was funny when I was watching the .0 is, and again, I also noted this to both Blue and Daniel in email, is that I thought, oh, there's these other papers that I've written that would have clarified or could have come. So very easily, this could have become like why don't you do 25 different papers? And, I think that might have become quite a burden. But some of my bonus slides that I know Daniel told me I didn't have to make any, or it's not typical, but I have some slides taken from some pieces of those other papers that might give some clarity to some pieces of your guys' questions, depending on which ones we start with, and this and the .2 of next week. So again,
Cool.
Thank you for having me. This is very exciting.
Awesome. I guess to begin, how did you get into cognitive sciences or cognitive modeling?
Oh, okay. The history, the origin story, right? It's interesting. So without going into too much and spending too much of the podcast on one's own life story, when I started out in computer engineering or computer science and engineering when I was a young undergraduate. I even came from like a background of art and digital arts, which is kind of interesting. I had learned to program late in high school, Then I'm entering in Bucknell University was where I went for my undergraduate education. And it was really strange. I did not do much. I actually did not know at all of machine learning, let alone cognitive models or computational neuroscience. It was more of that strict engineering education. However, I like to think that something that I did, which was I'm a philosophy minor, philosophy of mind is what I studied. I like to think that's what biased me and kind of launched me to where I am today. So I was always studying things like consciousness, also ethics and other aspects of philosophy and Greek philosophy. But philosophy of mind and identity was something that sort of motivated me to think, well, hey, maybe this stuff I'm doing in, hardware and engineering, I could combine the two. Is there a way to sort of emulate this concept of identity or consciousness? Little did I even know what the free energy principle. So then towards the end, I worked on complex adaptive systems. Again, nothing to do with machine learning. However, it ties so beautifully, especially nowadays. Over the last year, I've done thinking in working with Carl on the free energy principle and aspects of the Markov blanket. It's funny how all that construct ties back together. And it was like, oh, that stuff I studied years ago. Wow, it comes back into force, into play really, really strongly. And then grad school, I was in Dr. Seeley Giles's lab, who's actually a very well-known information retrieval scientist and a classical deep learning researcher. And then I was, and he was more artificial intelligence. But that's the reason why I got into deep learning. He gave me a survey. I was exposed to neural nets. He actually said to me years later, the reason he gave me that survey was to discourage me from going into it. But he told me he was glad that it didn't work. And then along the way, this is the part where the cognition comes in. I was co-advised by a cognitive psychologist, Dr. David Ryder at Penn State, who also worked a lot with another well-known cognitive scientist, Dr. Frank Ritter, he himself was advised by Alan Newell and Herbert Simon. So some of the greats of our time in cognitive science and classical artificial intelligence. So I was in the applied cognitive sciences lab as well. And so between those two worlds, I think that's what sort of solidified me to saying, hey, there's these big problems in machine learning, particularly with credit assignment. So I don't know, I'm pretty sure you guys are familiar with these concepts in one form or another, but credit assignment is just like when we're doing backpropagation on a big neural network, we want to play the blame game. How much does this neuron contribute in a positive or negative way to some cost function? And for some reason, that always felt at odds with me, because along the way, I worked with all kinds of really non-mainstream models like Hopfield networks and Boltzmann machines were actually my first loves, if you will. That's what I did in my early PhD thesis. So that was at odds with what's going on in deep learning, even though Boltzmann machines were used at the very beginning and then everyone threw them away. And so I think those ideas of like memory consolidation and memory storage and the fact that a Hopfield network couldn't remember everything, actually had very limited storage, was awesome to me. And I was like, I want to probe that more. Can I build systems with this? And so I was one of the early days working on Boltzmann machines, but like trying to sell them as the thing we should care about. And then towards the end of my PhD, so now I'm going to skip around a bit, I did work on recurrent neural nets with Thomas Mikolov. He's one of my friends. And then towards the end of my PhD, I had somewhere along the line over the years found predictive coding. My joke to my grad students is Rajesh Rao's and Dana Ballard's classical 1990s paper on predictive coding and classical effects of the eye was something that I read so many times that I said I slept with it under my pillow to hope that I would absorb how incredible it really was. So that paper probably was the strongest influence on why I decided, you know what, for the rest of my life, I'm going to do predictive coding. I think we need a lot of work here because it's, again, also not a mainstream area. It resonated with some aspects of Boltzmann machines for me because I love iterative processing. And I also read parallel distributed processing by McClellan, Rumelhart, Hinton. Jeff back in the day. And so all of those things kind of swirled together. And so that led me to saying I want to do credit assignment, but in a biological way. So backprop's got to go. It's clearly not what the brain is doing. I mean, if it turns out it does, I'm okay with being wrong. At least we explored some other parts in the space that was beyond backprop. And so I do like the Bayesian brain theory and the free energy interpretations of predictive coding. This is why I'm a fan of aspects of Carl's work. And so, taking that interpretation, that came a little bit later. I would say so after grad school or my PhD, I got faculty position at RIT. And that's where the free energy principle sort of biased me, and active inference a little bit later on. Actually, most of my students in my lab, if at least two of them that promised they would watch this stream, they both work on active inference. So we talk a lot about that or read a lot of these papers. And then, of course, very recently have I finally gotten in touch and I collaborate now, I would say rather readily now with Chris Buckley, who's really well known in active inference, Carl in free energy stuff, and Rajesh Rao was on the survey. So it was really great. If I actually did not give you and Blue, Daniel, that big survey that I recently worked with Tommaso Salvatore and Ankur Mali. But we have this big review of predictive coding over the last 3+ decades. And Carl's on there, Rajesh Rao's on there, Chris Buckley's on there, Thomas is on there. So there's a lot of really nice names, and they're really great people. And it was crazy when I got to talk to Rajesh Rao. Just as I told you earlier, I slept under the pillow with his 1990s Nature paper. So to actually meet him in Zoom was rather incredible. It was actually it was a fun experience to get to ask him even the questions I've always had on the tip of my tongue. And so anyway, that sort of is what molded me. And the cognitive science, cognitive architecture part, which we'll talk about in point 2, that was heavily biased by David Ryder and Frank Ritter, and my discussions with them and understanding architectures like ACTAR and SOAR, which are these older ones, as you mentioned, I believe, Daniel, or Blue, like in 1989 or in the 1980s, and what's the future, and we can have some fun chats about that as well. So yeah, I would say that because of that interesting blend, that sort of led me to say that I'm not just the guy that says we got to get rid of backprop and here's how we do it, and let's use the Bayesian brain theory of predictive coding or predictive processing to do that. But rather, let's use that, but also let's look to the common model of cognition, which is sort of like the grand theory or the blueprint theory in cognitive science that I've also sold my soul to. I was just at DC a couple of weeks ago at the Cognitive Science Symposium, one of the FSS symposiums for AAAI. And I was talking to Andrea Stocco and John Laird and all the greats from the old cognitive architectures or brain imaging and brain science. And we were talking about the directions where these go. So actually, if we talk about later the future of cognitive architectures, I might bring some of my thoughts from that really, really nice symposium. And and I could keep blabbing. I don't know if that really completely answered your question as to why, but I guess too long didn't read TLDR. Cognitive science co-advisor in grad school combined with an AI main advisor in grad school. Philosophy of mind in my undergrad strongly biased me with complex systems. And I guess I'll just blame Boltzmann machines, because honestly, those were wonderful, and I still think elegant little models that sort of said we got to look to things that don't work with at least gradients with the reverse mode differentiation algorithm that sort of characterizes backprop.
All the credit goes to Boltzmann in the end.
Always. Oh, and we should give Helmholtz some love too. Von Helmholtz and the Helmholtz machines, and those are wonderful too.
Well, Blue, if you want to begin with a question, or I'm happy to ask.
There was a lot there, so I could follow up a few times, but I am interested in what you said about the Hopfield network forgetting, and like how you thought that that was perfect, and like the most exciting thing that it didn't like recollect perfectly, the imperfect memory. Um, and I think that that's interesting to me also, and that kind of introduces variance, which we see like in humans. I'm a very much like it's all in your mind, and like I like to walk the tightrope between like perception and like reality, and like what is reality, and how do you like when you have a variant in a system, like because it forgot X, Y, or Z somewhere along the line, how do you find like the variant best variant, like what would, and then like, do you go on to selectively refine, like refining selective memory, and what would that look like?
Okay, so let me ask a clarification question. What do you mean by like variant model, or variant as in like a deviation? That's maybe some term I'm not quite, it's not triggering something.
So like in biology, you get variants, right? Like so you have like a biological variant, but I mean just as in humans, like you have 25 people at a party, and
Mhm.
25 you have 25 different perceptions and 25 different memories of that party, right?
Mhm.
And so in when you have like a network that forgets, what do you then do with that forgetting? Like what, you have 25 different networks, 25 different memories. Like how do you select the best one, or would you want to? And then how do you like what do you think could be the outcome of that? Why is that so exciting that you have selective memory in a network?
Okay. So I understand now what you're asking. To unpack that a little bit, briefly to answer why I thought Hopfield networks were so cool or so exciting, and just to make sure that I was clear, was the fact that they could only had like linear storage capacity. So as obviously you could actually calculate. I think it was even there's a formula with respect to the dimensionality of the patterns. You can actually say how many memories I can store vector patterns, especially binary patterns. Yeah, as I see the diagram being pulled up here, before things start getting corrupt. So I think that that was fascinating to me because I guess I had assumed that you could just store lots and lots and lots of information in these deep networks, right? And the fact that memory can be corrupted, it is a very human-like quality, right? We forget things, as you've brought up now, Blue, in your comments, and I think it is a human-like thing, but it also highlights, and again, later I would discover catastrophic forgetting in deep neural networks, which isn't really quite, at least in my view, human-like in the way that it happens in machines, where, and by the way, for the audience that may or may not know catastrophic forgetting, it's like you train a neural network on one task to predict cats and dogs, and then I move on to airplanes and trucks, and I learn to predict that. And then I say, hey, by the way, can you tell me if this is a cat or a dog? And it gets like 0%. It's abysmal performance. That's not quite like a human, because the joke I tell also my students is I'd be like, oh, as I learn to play the piano, I forget how to breathe. That doesn't quite work. So I think now tying that back, so that again is like motivation, and I actually have like a bonus slide to say like future directions. This is like one of the things that I've been working to try to resolve with biological models. The Hopfield network was interesting in Boltzmann machines by extension, because they're just Hopfield networks with latent variables. I like the concept of attractors. So when you build like a Hopfield network, the idea is that because you're learning with contrastive heavy learning, which was also the algorithm that really caught my attention. I love that idea of just, hey, I find equilibrium, I run my model for like a certain phase, I compare it to some clamped phase, and then I just do a big subtraction, you get Hebbian rules out of it. That's like one of the central reasons too I liked Hopfield networks and Boltzmann models. But these idea of having these attractors in space, where if you could figure out your optimization landscape, usually it's an energy landscape, with a Hopfield model. We are pulling the data, let's say templates even, or representative aspects of data at these little pins that are saying these points in the energy landscape are what I'm going to remember, and patterns that look similar. So I guess this might kind of slightly address your comment on a variant. So variant as in like variations to particular memories. If I meet someone or I have certain attributes in a vector, this would fall into this dynamical attractor, right? Which again would fall into this energy landscape. I really like that interpretation of how memory works, because then it's not just me storing things in a hard array, right? The idea of like, let me just store every vector I've ever seen, because now you have this problem of capacity. And then again, how do I build and there's some value in modeling things in that way. So this isn't a criticism of any neural models in that regard, but I like the dynamical attractor kind of point of view, which again, then you can connect it nicely to free energy and say, oh, it's your free energy functional. And I am just walking along my landscape to plot my memories in there. So I think that's what fascinated me, was the energy-based interpretation. And then again, Boltzmann machines and restricted Boltzmann machines, also known as harmoniums, they have this beautiful kind of energy-based functional interpretation. And they too are recollecting patterns, right, by this, you could say a dynamical reconstruction, but it's really just like I'm clamping noise and I'm running this until I reach equilibrium. And that sort of retrieves from my memory some particular element of life, right? Something I've experienced in my niche. And I pull out that attractor, or I basically am just saying how similar I am to that attractor. And then, of course, later on, there's been a lot of more efficient work, and then there's criticisms of Boltzmann machines. But so I think like that's particularly why I found them specifically fascinating. I'm going to stop myself there. I don't know, Blue, if that was scratching at least at some type of answer to your question.
That was great. Thank you.
Earlier, you mentioned this grand cognitive science framework, kind of the general cognitive model. So how do you pursue that, or where do we place or enumerate all these features of diverse intelligences like memory? But clearly, just in your answer, there's multiple implementations that are non-overlapping of memory, almost to the point where it's like, what can you really say memory even is? So what are those core pieces, and how will we know or assess that we have the relevant even continents sketched out for worthwhile pursuit of anything other than just an abstraction?
Well, I mean, wonderful question, complex question. And, I'm not the only person. I mean, I'm just but one small voice, right, that, should speak to that. I think all the great cognitive scientists I've even just met in the short span of my life have some interesting differing thoughts. So I think just to clarify what you said, Daniel, the grand kind of blueprint theory that I'm referring to is actually well known. There's some nice papers. I can try to pass them on to you in Blue if you don't already know of them. It's called the common model of cognition. And by the way, it is not the only way you can build a mind. It's just the one that resonates the most with me. And so I just want to point that out. It's not, again, just like anything, there's no such thing as a silver bullet. I would even venture to say that there's probably a no free lunch theorem that applies to cognitive science, just like I teach it in machine learning. So there's probably no one cognitive architecture, because I think Blue said it, but you might have said it, Daniel, about modeling things that are not necessarily human, which I think could have generalized to animal cognition, but it could also even, my brain weirdly enough went to alien cognition, right? Things that are not even of, planet Earth. Maybe there's other types of intelligent organizations. And I do believe that there is probably more than one way to build an intelligent computational entity. But without getting into that, also potential can of worms, the common model of cognition, I think, to sketch out what you said, lays out the continents of the mind, to use your word. The reason I like it is that it sort of is like a synthesis. When you read the paper, they themselves at the time, this was now years ago that the original Common Model of Cognition paper came out, and they looked at things like ACTAR, SOAR, Sigma. I don't know if they looked at, like, for example, they might have looked at versions of Randall O'Reilly's work. He does a lot of really nice stuff, like Libra, the Libra architecture. I don't remember if that was in there. And other variants. Of course, I don't think they had like Chris Elias Smith's group at Waterloo, who did the work on Spawn. You might have heard of NANGO, which are like spiking neural model toolkits. Spawn is an SPAUN, Daniel, if you want to write that so that way, because there's like a science paper that he had years ago that came out about Spawn. But they looked at maybe not those specifically; those would be like the updates. But they looked at particularly the first three that you have in your notes there, and they synthesized these architectures and said, what are commonalities here? What are they trying to model? And I sometimes I misuse the word brain regions, but rather it's more like functional continents. I'm going to borrow your terminology, Daniel, of the brain, and they kind of chop it up into saying, well, what are the grand pieces of computation that goes on? And let's see if I can distill it from my own limited memory. We have our motor functionality, our motor cortex. We have perception. And of course, now I, of course, have added my own addendums to that, where you could break up perception into modalities like audio, visual, and then, of course, olfactory and touch and taste and all these other elements that maybe we don't model very well, but we'll leave that, again, also as a separate discussion. And then the parts of memory. So we have, for example, procedural memory, then we have declarative memory, and we have working memory. And those are kind of like the big kind of groupings of all the other things inside of there. There's different types of memory that you could start partitioning up. And so like declarative memory would be like fact-based knowledge or world-based knowledge. It could also include episodic memory, which is kind of blobbed into there. And I've done some work on modeling episodic memory because I do things with active inference as applied to reinforcement learning. So of course you need, at least a type of replay memory to sort of refresh your, statistics. I'll leave that vague for now. And then you have working memory, which are, again, this could be a bias on my end because I have studied things like ACTAR, but they're like buffers. So I think of working memory as not just this one module, but rather many little tiny occurrences of this module. And they are the glue that helps transmit information between various continents in the brain. And then we have procedural memory, and procedural memory is really interesting to me. And I think it resonates really strongly with just because, again, you're the Active Inference Institute, and I have done research in active inference. So, because I remember a question you had, Daniel, on point zero, you said, where's the action? And then later you guys answered that question, actually. But just to be clear, there's other papers, too, where I try to show you how to do active inference without even a cognitive architecture with predictive coding. If I ever show you these bonus slides, we could look at some of that. But anyway, and procedural memory, I think, resonates really nicely with active inference in the sense that I put in there its dynamics model. So again, if we imagine we have perception and we think of that as, the context of active inference, which is usually a POMDP, partially observable Markov decision process, let's assume that Markovian assumptions are okay for now. I have criticisms of that, but the idea is that we have our input space, we have a latent space. That's what your cortices are doing, right? Like the visual cortex is transforming beams of light or pixels in a computer into some distributed neuronal representation, ideally very sparse. And this is, again, I know Blue's very interested in my aspects of sparsity, which is something I'm obsessed with. And I think we all should be obsessed with because that's very biological. And then if we put the motor cortex as like, well, it's going to take other signals, and that's where the action comes in, Daniel. So like, for example, motor cortex is going to take information from probably information processed in the cortices, maybe information queried from various pieces of memory, transferred to the working memory, and then they'll do something, and then we'll get our our signals, whether they come from another part of the brain, like the prior preference part of the brain, which is kind of like our, our goal-oriented signals. And then the part that, again, to go back to the procedural memory, the dynamics model that lives in there, or the way that I've been modeling it, and I do this in CogNGen, but also I just do this in my robotics work too, is that's kind of living in latent space, is trying to guess the next state, the sparse distributed state of predictive coding circuitry. And with that, it's saying, oh, I'm wrong. You get the basis of an epistemic signal, right? And that's how you encourage foraging, right? Because exploration is, like, to me, my view is the real crux of active inference. If you don't have foraging, you don't have this epistemic kind of signal to drive you to be curious about the world. I know you guys have talked about curiosity, but also the prior preference and obviously plays a role, because you could either encode goals. And if we're doing RL, we sort of do it like, oh, well, we could use the reward function, or maybe we train some prior model. But the other way to look at that is that's where also like homeostatic constraints could be, embodied. And that's the stuff I'm doing with Carl now. I'm going to have a nice big paper that's about to come out once I finish applying some of his edits, and it'll basically address that, the life aspect of this. But put that aside, because it's another can of worms. I have lots of can of worms to avoid. And then the last piece of this puzzle is inside procedural memory. There's the basal ganglia, which is another structure I'm very obsessed with. That in the prefrontal cortex, and these particular constructs in the brain, they do many things. I mean, the basal ganglia is often, cited and studied for like dopamine application and reward injection. That's where the reward signals come. And, I've often used that interpretation. But another thing, and this is why Andrea Stocco, who's at the symposium, and I really enjoy talking to him, has done a lot of study of the basal ganglia. He has put in his work, and he has found neuroscientific evidence of it being like an information routing system. And that, to me, is a humongous tool for tackling catastrophic forgetting. Because the way I see it is, if I have this neural structure that is responsible for deciding what task I'm in the brain, or what pieces of information should play a role in the task that I am doing, it's like suppressing regions of neurons and exciting other regions. So it also induces sparsity, to tie back to sparsity, at the most extreme level, right? It's like turning off parts of your brain and saying this is task dependent. And the prefrontal cortex can be argued to do some of this too. I haven't modeled that specifically, but I've seen other people do that. But again, the basal ganglia was one thing. And so I have work on that you guys aren't also talking about. But again, I've already thrown too many papers at you. But focusing on just like, oh, can I do information routing with some basic predictive coding circuitry? So I think that sort of big glut of speech that I just threw at you guys sort of gives you an answer, Daniel, as to like why the common model of cognition is so nice. Is what I just explained was I just used their blueprint. I mean, they didn't say the mechanics and the active inference part. That's my twist to it, right? Can I reinterpret common model of cognition through free energy? The answer is, well, I've bet everything I have on that idea. And then, and I teamed up with someone, Mary Kelly at Carleton University, and she works on, for example, Minerva 2 memory and hypervector symbolic structures and holographic memory and hypervectors. And that's where, even though I know Hopfield nets, that's kind of another world that, they sort of intersect. So we put that in there too. But I don't, that's, maybe we should save some stuff for point 2. But what I just explained is I walked you through the blueprint, which was very vague. It just said we should have these grand continents, and they might do certain things. They have like little arrows in their diagram about information that's transferred, what modulation is going on. But then they leave the implementation level kind of vague, right? The idea is it could be whatever you want. You could implement it even classically, like in the 1980s with, production systems and if-then statements. Yeah, this is a good diagram, actually. And you can kind of see some of the key aspects of memory here. And again, too, what's nice, I took from Common Model of Cognition, and I do have a slide here. I keep saying I have a slide. Maybe I'll show you one just so I can prove to the audience I do have them. The idea is that the action element, the active aspect of active inference, Common Model of Cognition also speaks to, right? It says, well, we have to have a motor cortex. It doesn't tell you what to do with that motor cortex, except that it's going to, produce some motor command, and then, it will transmit to the body. And we'll leave embodiment as another thing. That's another can of worms that I have been trying to address. And inactivism, which is your niche, and how that relates to this. But let's just zoom in on the architecture of the mind. And it has all these components. So the way I envision the future, just to tie this to another question to make sure that I'm not just blabbing, but keeping us, useful, is that I think the direction we're going to head, or should head, I don't know if everyone else will follow that, is that you want to build these biological cognitive architectures, rather than just, let's rely on a production system like we do in ActArt, which is valuable. It's not really a criticism of that, because maybe the level of modeling you want to do is, I want to encode this knowledge. It's a lot more intuitive sometimes to encode in like if-then statements and logical statements, as you did in classical architectures. You can interpret it easier. But the part I think that we really need to push for is, how do we get that type of behavior, that type of self-organization, without me hard coding this knowledge, right? Because again, it gets to expert systems and good old-fashioned AI. We kind of don't want to be doing that. We want to say, can we do this in a neural way? And then the answer I try to jump ahead to is, I say, by the way, don't do backprop, because while you could do backprop, and there's, I think, work on people trying to build types of cognitive architectures with that. At least it's a better step than ChatGPT and claiming that solves cognition, because it doesn't. And I am in that camp. But again, leave that can of worms somewhere else. But the idea is that you skip that and go into something that's biological, which is predictive coding. There are other things you can do. I actually am working on other things besides predictive coding. Maybe we can chat about that in future directions if that question comes up. But I think predictive coding and predictive processing offer you a lot that, other algorithms right now might or might not give you. They might have drawbacks. And this could even help answer, if the question comes up, Daniel, if you're interested, like, what aspects of neurobiology does that bring to the table? But I also think it has the best way to convince machine learning individuals is to explain the practical elements of it. Because, a lot of times they'll say, well, who cares about modeling the brain? I just want to build an intelligent system. But you can use predictive coding and predictive processing as a pragmatic type of argument, and you can say, hey, well, you get this, you get this, you get this, and among those arguments is sparsity, but there's even more powerful pieces that we could go into. I think I'm going to stop now, because that's a lot of information. I don't know if I missed any piece of your question.
No, it's great. I'll ask a short question from the chat. Viet writes, can we represent declarative memory with neural network-based techniques such as Hopfield net?
Did you say Viet?
Yes.
That's I believe that's one of my students. Yeah, he's also works on active inference as well. So I'm not surprised that he would throw a question like that. The answer is yes. You can, actually, there's a lot of good work already, even without the cognitive architecture kind of structure. Because again, think of the common model of cognition as like a blueprint that tells you what things you're going to need to have and how they interact. But if you zoom in on one of those continents, declarative memory, as was pointed out in the question, For example, you can use vector symbolic structures. You can use, for example, Minerva 2 memory. There's a lot better. I would recommend faster models, which are Hebbian-based systems, right? You can model Hebbian memory, associative memory, heteroassociative memory with a lot of these like simple kind of Hebbian-like constructs. The learning is very efficient as well. They don't come without the drawbacks, but so the answer is yes, and you can model them with, I think, Hebbian networks, Hebbian learning, which is a correlational local learning rule. The other part with the hop field network, you can also do that. And it's weird because while the work I have currently done said we will do hop field networks in our cognitive architecture, which we'll probably chat more about that in point 2, CogNGen. But we do have plans to do like, what do you call it? Modern hop field networks. That's a particular instantiation of hop field nets that is actually very efficiently implementable, as I've discussed with my collaborator Mary and others like Robert West at Carlston, talking about these types of things. But you can use a hop field network to sort of use to create that dynamical attractor interpretation I was telling Blue about earlier. And the idea is that, it'll have a certain capacity, but the problem is we need to make sure that we have enough capacity because, again, I don't think I ever completely properly answered Blue's question about variance or, differences between what's, reality versus what you think reality is. And there's some interesting connections to predictive coding that also answer that question. But the idea is that if you have one single hop field network, that might not be enough, but I imagine chaining a bunch of these together to create what I call an assembly or an assembloid, to use one of Carl's words. Assembloids of hop field nets, I think, is one way to build a completely neural implementation of declarative memory. Another piece of declarative memory that we did model, I won't argue it was the most efficient thing you should do, but it can be done, is Minerva 2. And again, that you can look it up. It's Hintzman and all, and Hintzman's old work. It's an approximation of a large Hebbian auto-associative memory. And what we did is we modeled the episodic memory with like a big Minerva 2. The reason I say it's not a good idea is Minerva 2 is really slow because it's kind of like approximating this Hebbian associativity with like a weird echo query style lookup table. At least the implementation, and even when you vectorize it and put it in TensorFlow or your favorite linear algebra backend, you can only get so much of a speed up. So for very big memories, I don't think that's the right place to do it. But the value of what we did is we essentially tried to emulate what episodic memory does when you do replay and reinforcement learning, right? So you have to do some weird hacks to make the episodic memory predict the next thing rather than recall this thing from a corrupted input vector. That's called heteroassociative memory. And we did some things with like a window, and we said, hey, have this predict the next latent vector, since I told you we live in latent space in the cognitive architecture. Maybe predict what you thought the original action you're taking and the reward, and we sort of use that to roll out little streams or mini streams of episodes, and then we use that to train the modules that are inside the cognitive architecture. For example, if you do replay, you can refresh the dynamics model, you can refresh the motor cortex, because again, you're querying this episodic declarative memory to say, hey, remember these little tiny mini experiences. The other problem with Minerva 2 was that you can only remember so far into the future, so it gets a little wonky and hacky when you try to build like these like little lookup windows. But there are better memories out there, and actually my collaborator and I've talked about using modern hop field networks as one possible construct, and they're very cleanly implementable. They almost look like autoencoders, which is kind of crazy, at least from like the engineering point of view. And so once you understand that, you're like, oh, I could build all of these and build, again, what I said earlier, assembloids, right? Or assemblies of these hop field network structures, right? And maybe see what those do when I want to recall particular pieces of experience. So that would be the answer to your question. I would say I only have some experience with the episodic piece of declarative. When it comes to like the world fact, graph organizational knowledge, I don't have much to say yet. I know you can use Minerva 2 and vector symbolic and holographic memory and hop field memory to emulate that. People have done that on, like, for example, language tasks. Another really nice name, and he's done work on, I don't know if you guys in the Active Inference Institute know him, Ben Goertzel. He's, a premier researcher in, okay, Ben, I see you shaking, in AGI, right? And he has OpenCog. And I know that he's done some really nice work on graphs, knowledge graphs. And there's people that have had discussions with him about neural implementations of that. Because when he and I have talked, and I also work a bit with him too, I've said to him, okay, well, what would be the like purely neural version of this? And there are ways to do it, whether it's simulatable in our, computing systems nowadays. I don't know. It can be expensive, but it can be done. So OpenCog might provide a nicer, cleaner answer than I possibly could today about like the world fact knowledge in graph organization of how we think about concepts. And I think OpenCog has some of that answer. But again, I'm going to speak with that as the final statement and boundary of my knowledge, and let the audience look into that. But I do recommend Ben Goertzel's work in that area too. So Robert West, Ben Goertzel, these are some really nice names to kind of look at how they either use the common model of cognition, or they build their own cognitive architecture and they model certain pieces of this structure that have nothing to do with, let's say, predictive coding. Because Ben, the reason he's working with me is because I've said, oh, we should do it with predictive coding. And he was like, that's a great idea. And so, hence collaborations get born. But so, yeah, and obviously, and as Daniel's writing that statement, you'll notice I'm extremely biased, but I think with rather good reasoning. Even from a neuroscientific point of view, there's a lot more evidence for predictive coding than there is for backprop in the brain. Plus, you can approximate backprop with predictive coding if you squint at it and make the right theoretical assumptions in the right way. So obviously, I'm going to say everything should be built with predictive coding. And then also the beautiful thing, and I know Carl will like this if he ever watches this, is then you can also state it's optimizing or minimizing a variational free energy, and we can derive where that comes from. And it's a Bayesian model, right? And so you have this Bayesian graphical model interpretation, and it's a really, really elegant framework too. So that's another strength, I think, of predictive coding. I guess I am the market man for it now, but I really do believe in it, and it's served me well over the last, as I'm coming up on almost if we count grad school, almost on a decade of working on this. And I do think predictive coding is at the forefront of where we need to go if we want, biological, human-like even machine intelligence. And I'm going to stop there too, because I don't know if there's more questions. I can keep going very easily.
Yeah, it's awesome. Very encouraging. Certainly, you lay it out differently. Everyone does, but you lay it out very differently. It's actually very rare to start on a high road. It's not exactly the high road laid out by the free energy principle, but this kind of approach to cognitive science, which is like, let's sketch out the functionalities and then drill in. That's how a big tent is built, because it clarifies that there's all these different implementational techniques, none of which can be all things in all settings. And then another piece that the work holds up is what's biological, when after all the neural network is the great-great-great-grandchild already of a cell type. And so what is modern and biological? And then it just made me think about how there's the pure biomimicry, which is usually like if somebody were actually interested in studying that system to resolve some pathology or just to do natural history. And that's one sense that we might be doing biologically inspired computation. But whether it's leaving the door open to our alien colleagues or developing new synthetic intelligences, we need something that's both biological but also novel. And then this leads to consideration of, well, what are the fundamental constraints other than the historiosity of the life forms today with 2 wings or 6 legs or whatever they may be? What are the real features? And that's where we complement those fundamental attributes identified by the common cognitive model, like memory, action selection, and perception, where those come together with like local processing only, and then also some more potentially aspirational things like low energy compute and other features. So these are just some big topics, and it's kind of like, come work on it. These are the challenges because they're laid out. The challenges are not esoteric at all.
Oh, we've either known about some of them for a while and just never resolved them, or they're becoming more pressing in today's day and age. Like you brought up the energy compute part, right? And energy efficiency, and we had global warming, regardless of whether or not you want to, accept it, is upon us, and we have the problems of even in AI. There's this thing called green AI versus red AI, and I've written a little bit about this in some of my papers as a motivation to look into biology, because the brain is, regardless of its own limitations, every biological system has trade-offs that it has to make, but it is an extremely energy efficient system, and it's an example of beautiful parallelism as well as low energy compute. And if we could get even just a little bit of that in our systems today, that would be huge. So I think that's a nice motivation. Of course, I also work in, I know you guys talked about one of my papers, spiking neural nets, which gets us into neuromorphics and neuromorphic computing. And I think there's a lot of really nice hardware in silico that's out there that we could take advantage of. But the key is finding the right algorithms that we could implement there and carry over the best of all the worlds, right? The best principles that our software simulations and mathematical arguments make, but then instantiate them in, let's say a memoristic crossbar. And I've worked and talked with different people, including Intel's Loihi chip, and I'm not saying that there's many different ways you can build these constructs. So, and I know that because I've watched some of Carl's chats with you guys and talked with Carl about this. Is also, I do think the biological chimeric implementations is like a really cool area. I'm a huge fan of organoids and organoid intelligence. I think that's a humongous place. That's like a new frontier almost, given like Smirnov's work and a couple other people. And I think that's where like these ideas of predictive coding and the computational models we build are valuable to even consider in these biological systems. Either study them and see, do they match back to my mathematical theoretical predictions, or can we manipulate or engineer them to, maybe induce similar kinds of compute, or maybe we'll just see that it pops out. Maybe they're just doing predictive coding and we're going to see that these neuronal structures emerge, and I think that would be fascinating. A quick point I want to add, and because I see Blue raising her hand, so I just want to mention that the thing I like about my interpretation of predictive coding, and it's not only my own, it's just that I carry that forward, is predictive coding, as I've talked to people, is interpreted in a lot of different ways. Like in psychology, predictive coding kind of has similarities, but it's not quite where I work, which is the mechanistic version of predictive coding. And it's interesting. I think you can borrow those worlds. Like, hey, the idea of predicting error and feeding that back in, or matching discrepancies, in our memories. That's a beautiful concept, and that's, what psychologists look at. Cognitive scientists kind of see things in that way. Biologists and neurobiologists might sometimes talk about predictive coding, but they might not necessarily mean it like in the concrete ways that my work, which was inspired, by Regis Rouse and others, to say, let me build you the exact mechanics and the dynamics. And I think that's important to get right. I am, even though recently I'm getting a little more philosophical, which I love, and theoretical, in talking to Carl and others, and Ben, there's this engineer in me that cannot divorce away the very specific dynamics and the not just the mathematical, like, oh, the ordinary differential equations, but how does that get implemented efficiently? Because I think that's what lies in the future, is the marriage of these kind of high level theoretical, mathematical, philosophical concepts, their mechanistic description, which is what like predictive coding says, hey, one set of neurons tries to get another set of neurons firing rates or their activities, and we can feed that back in, and you can repeat this motif and build very beautiful constructs like what I try to do in cognitive architectures or little POMVP systems. And then we also have the spikes, right? How does that compute happen at this very fine grain level? And then how does that get put onto a chip? And then I think the other piece that, and then I'll shut up, is the connection to the niche. I think it goes back to the body, and you can't ignore the body. And I have a lot more to say about that, but I'm going to bite my tongue for a little bit because I want you guys to read that paper. Maybe we'll have another chat in the future about it. Carl and I have really thought very deeply about this, the role of the body, and that has nothing to do sometimes with neurons, or at least not the neurons that we model. And then the niche itself, and how does that have a role? And then I know you can go into, and I know all the cognitive theories like extended cognition, embedded cognition, how do other agents and cultures and tools play a role, the extended theory of mind, because I did study that as a philosopher. So I think like those parts are those all need to be reconciled and build this kind of framework. And I think, Daniel, you're right. You can use blueprints like the CMC as a stepping stone. And I think that top-down way is a nice way, but then you also merge it, right, with all this bottom up. It's kind of like you're doing predictive coding, but in the scientific realm, right? You have this top-down kind of direction you want to fill, but then you have all this mechanical, low-level stuff that you really can't ignore if you want like energy efficiency. And where do they meet in the middle? So it's a bottom-up, top-down, which is beautiful because it repeats the metaphor of biology. And I'll stop because I see blue. It's time to let someone else speak. You had did it.
Go for it,
You had a
Blue.
question. Yeah.
So you really like stole my thunder there.
Oh, sorry about that.
It's okay.
I have a lot to say sometimes.
It's okay. No, it's perfect. So I really wanted to ask about the role of the niche, and especially like when we're talking about like energy efficiency and predictive coding and the compute power, etc. Like I think about like what makes us efficiently able to do cognition, and it really is like cognitive offloading into the niche, like the internet, the phone, like click, click, click. Now I know this, right? And then even like with non-human systems like ants, like leaving pheromone traces in the environment that convey a ton of information as to where to go and what to do. And so how can we then bring the efficiency of cognitive offloading into cognitive architectures that we can then leverage for increased compute power with very little effort in terms of like the actual compute?
So the answer to your question is extremely hard, right? It's a grand challenge, if you will. I would say that the right path, and these things are okay for me to share because thankfully they're not all of my invention. So to think about how other agents and other tools could be efficiently used to allow our own agents, right, our artificial agents to achieve their tasks, you do need to now finally answer the question of the body and the question of the environment. And I've been thinking a lot about this, and let's just assume that you can simulate it. That's another issue in of itself, but you pick your world, right? So let's say I'm going to, I'm going to start with my body. I'm going to do a quadruped robot, right? Like, what is it? Big Dog or Spot, right? The little robots that are out there. And that's going to be my actual morphological construct the body in which that I'm going to manipulate it. Now that body, let's assume that I have access to all aspects of its physical mechanics, okay? And its artificial hard-coded routines, because robotics have a lot of like automated procedures. Like you're not going to necessarily need to manipulate every piece of the arm. You're going to use take advantage of inverse kinematics and other algorithms that allow you to say, I just need to move this point and the rest of the arm will kind of coordinate around that. And that is an offload of what the neurons need to do, or the neural compute. And let's say organized, and I'm a fan of common model cognition, so let's assume you build your little brain from the CMC point of view. That's going to, again, not worry that much about the fine-grained mechanics of the pieces of, let's say, the quadruped's front right arm, right, or front left arm. It's going to offload because it knows that as long as I tell you I plan to move this piece of my, joint in this direction, the rest of the arm is going to follow along. You've already now done embodiment, which is embodied cognition, which says and I'm on the extreme end. There's like spectrums of, I've studied cognitive science. There's the body kind of influences the mind. Then there's isolated cognition, brain in a vat, and then there's really strong embodiment, which is the body does a lot. And the brain kind of just says, hey, let me send you a little control signals to manipulate you. So that's the embodiment. Now we get to the niche. And by the way, so I've already started to answer your question because I picked a body. You're going to need to commit yourself to a construct, which, by the way, means you're not as general as you would want to be, but it gets you a chance to answer the question, because now you say quadruped. Now you say, what's the niche? Where's that quadruped going to operate? And I don't know, I'm going to pick something really simple. Outside my office, there's, some hills and some grass and some trees, and I'm going to specify this little world. Maybe I'm going to design some way of recharging that robot's batteries, because obviously we need to create some type of life-giving force, some resources for this to look for. And I specify other properties of my environment. Now I've specified my niche. Now I've answered concretely the exact world that my quadruped is going to operate. So now I know the inactive cognition comes into play, right? Because now I have to interact with the physics of my world. It's going to manipulate the robot. It's going to damage the robot. The robot's going to have to respond to this. So remember, under the hood is like a CMC neural predictive kind of neural construct. It's offloading a lot of its cognition to the body. The body says, oh, I'm going to also take advantage of sensors that I can read in my environment. I know, I don't want to be maybe in a very hot area that starts to, interact badly with certain properties of the robotic construct. And then to now get at the answer to what you said about other things. Well, in this world, I should also, and I think there's some work in, I cited it in the one paper that's going to come out, about tools. You have to specify what are objects that are manipulable. So you need to define your affordances. And by the way, this is, again, defining the niche. I think it's really important not to just say, oh, I'm going to throw it in any environment and it'll work somehow. You need to define the properties of your niche to some degree, because that's how we can also experimentally analyze and study what's going on. And you say, what are the affordances? What are things that I can do? What properties of the environment am I able to manipulate that I, let's say, even that could help you model this? And then you introduce other quadrupeds with the same exact underlying cognitive structure, because let's say we're not going to do heterogeneous multi-agent systems. So, I introduce a couple other spots, right, which are also operating under the same principles. They minimize their variational free energy inside the common model of cognition. They have the same, roughly, artificial dynamics that they can offload to their robot bodies. And they could work together, right? They could create herds, right? They could have herd behavior or group behavior, because maybe now they're going to find those port charges or whatever the resources is that I allow them. Maybe they're solar powered. I don't know. I mean, they have solar panels and they need to collect from the sunlight. But obviously, if it rains, they need to hide. And so you can now say those dynamics, those groups, now they interact. Maybe one of the spot bots found a good area, and this is a really good place to exploit their prior preference, which is, to survive. Hey, I want more energy. I need to just continue living, right? Because I think life is the place you have to look. They don't want to die. They don't want to terminate. So they're going to work together to do that. So that answers the embedded part, right? Because the embedded aspect of it is the cultural, and this is an approximation. I'm not going to claim that a little herd of quadruped spot bots, right, are going to have a society. I don't know. That's an emergent property, perhaps, but they'll have some means of communication, and that way allows them to organize themselves as their own little system, in their niche. And then, of course, because we specified the affordances and properties in the environment that you can manipulate, you have extended cognition, right? Because these tools allow them to better survive, better find those areas that, for example, allow them to charge their batteries or, collect sun at the right times and avoid damage from the world, when it's raining or when there's inclement weather. And again, I'm kind of like vaguely describing a very complex niche. You could really experimentally control it. Maybe you make it a lab and, you have artificial blocks and charging ports, and maybe you could kind of simplify this a little bit. But I think that's where that doesn't give you the exact answer. Because, if I had the exact answer, I probably would have implemented it and we would have solved AGI, right? But I do think that's the pathway to answering your question, right? It says, if you want to even have a chance at scratching at the answer of efficient interactions with the environment, using objects and tools to solve problems and offload your cognition to these, let's say, non-neural, non-biological entities, or these non-living or let's say, planning entities. I know Carl talked to you guys long ago about the difference between the environment's also its own system, but it doesn't plan. But it's subject to thermodynamic constraints, and the entity itself is also that one is different because it can plan. So there's a little bit of its own ability to change its outcomes with planning as inference. So you could kind of use that as your starting point to say, I need to define the niche. I need to define the body. Then I need to define the organization of the brain structure that goes into that body, because you do need to have the neural part. If we're interested in modeling, let's say, very high level cognition and behavior, and how does that interact with the hardware? And that's another question in of itself that I've been thinking about. And I think with all of that, you get a chance to now simulate, do experiments, and actually see how does that efficient interaction emerge, right? What can we study aspects of embedded cognition, right, into this little experimental niche and agent niche and collective agent niche setup that I've constructed. So I think that's an interesting place that this is where I would go, right? And I'd love to go if I had the resources, but I think that gives you a chance to begin to answer that question, and it'll tell you what's wrong with a lot of things too, because I think it'll say you're going to quickly, especially if you just even pick the body and you're doing embodied cognition, you say, hey, wait a minute, this neural construct, let's see, backprop, right? It isn't working very well, right? Because why? I need to unroll in time. I need a time machine to do backprop with time-based data. But predictive coding doesn't really need that, right? Oh, well, probably that might be the right neural structure for the brain, because now it interacts with my robot hardware, which has very limited resources. You have very limited memory and compute that you can run with. So already there, you've now manipulated your software. You have now co-designed the hardware and the software a little bit to interact in the context of this morphological construct, your body. And because you've also defined where it's going to operate, you also understand what properties of the environment you need to be aware of. Maybe you can build that as an inductive bias into the system, because we don't want to play evolution, because that's usually how you emerge these systems. But I don't know if I want to wait doing genetic algorithms for, whatever simulated thousands and thousands of years. So maybe we need to build those inductive biases as well. And that's another interesting research area. And I think now I'm digressing, so I'm going to stop there.
It's great.
Is that
again?
Something blue? Oh, sorry.
Oh, just the pathway is clear. And in fact, this is even in some ways an anti-reductionist pathway that actually starts from the bigger context. You stepped through specification of the niche and the context, getting to the embodiment, including the extended embodiment, pheromones and all of this with a niche. Like each time you step through, then to the brain and the body, then into the multi-agent. And then that is where the evolutionary and the ecological dynamics kick into play. Eco, Evo, Devo is going to pick up once there's like a population, even if it's an in silico population that has resource constraints, or it actually is a materialized system, then the ball's rolling and it either persists or doesn't. It's like a landing strip for our efforts and a organizing principle for our research, whether we're like just beginning to do cognitive science research and thinking about going to grad school or something, or trying to recap on this flurry of development over the last years of being aware for a long time. It's actually to me a mark of the advancement, not just like how fast or performant the systems are, but how many index card type agreements or ways of coordinating that we have. We have the common model. We have, of course, active and free energy principle, which we've barely talked upon. We have this kind of general agreement of the structuring of cognitive systems. And then that organizes otherwise what would be essentially arbitrary, unlimited information, because the scope of cognitive sciences is so vast that having some of these categorizing strategies as part of our recall system is part of it. And then that's an interesting question about jump starting it. And what do you bring to zero? What do you bring to the table? And then we're the agents with our tools that are building other agents and tools, and all of the like reflexivity and also relevance that comes along with that.
Yeah. Yeah, I like that summary.
Blue,
I could go on and on and on about it. I even have different names for these things, but I want to. There's a little bit of thunder I can't steal just yet, but I will ping you guys. I have a couple of people in mind about sharing a manuscript I've been working on for many months at this point, and this is related, especially the relationship between neurons, the body, the environment, and beyond, and how that all ties together. So this is stuff I've been thinking a lot about. So it's actually timely. Your questions are great. I didn't know we'd get into this part, but it's fun. And there's more to the story too. There's other, but I want to save that thunder.
Yeah, dot three.
Maybe you could have me on about that paper if you ever read that, but that's a different thing.
56 never dies.
Exactly. He doesn't leave us alone.
Or like a sequel, like a one paper sequel, because I will say, like, four papers was challenging, and I don't think we've really we've skimmed the surface of each paper, but like not even, there's so many interesting threads to untangle in just what we've talked about here. And like, are you sure you don't want to go into evolution? Are you sure?
I'm not opposed to it. I think the problem is space sources, Blue.
Yeah, no, I don't know that genetic algorithms is necessarily like the way or the means like that I mean, but I really am curious about like unraveling maybe alien cognition. Like, what does that look like when I really start to think about like what is the most different kind of cognition that I could imagine? What is the most different from my own? Like, I really think about plant cognition, and then like active inference becomes kind of problematic because they're really limited. They have a really restricted like course of action, right? But I think about like what, how plants have evolved and how they've co-evolved with humans, like, and how they've, they produce all these lovely things that we like to eat, and they produce things that alter our own cognition, so like they can totally drastically influence our information transmission pathways, and I really think about what does that cognitive system look like, or what is it like to be a plant, or to have a memory that looks like a plant memory, right? All of your memory is essentially chemical, like, or evolutionary. And I think about that in terms of like why like evolutionary memory might be important, and across species and across, you know, evolutionary time, like not necessarily evolving through genetic algorithms, but what does that evolutionary memory start to look like?
I mean, it's a great question. Well, I don't have any work of my own. Well, I have worked weirdly enough with, by the way, I will say I have worked with neuroevolution. Actually, you guys had, I know you know the ant colony paper optimization with Abdelrahman and Travis, right? I was in the audience and I chimed in and talked to you about active inference. So I have hedged my bets a little bit, you know, to look at other ways of doing things. So while I did say I sold my soul to predictive coding and common model of cognition, I guess it's not completely the truth, because I do look at other things. But I do think that it's interesting, Blue, that you bring up about things that are not human or even maybe animal-like, right? Because there's also animal cognition, which is, there's some differences. So when you go into something like plant evolution, it's interesting because there is work, as I have found. Again, I want to say it in a way that, again, I don't steal too much thunder from this one paper. I'm like it's on the tips of my tongue, you know, and it's like, hold. It's almost done. I got to finish the edits, put it on archive, and then we can all chat about it. But there is a dressel of plant cognition and, like you said, alien cognition, or just, let's say, non-human cognition. And this work's existed. It's wonderful work to read. Have you guys heard of the life-mind continuity thesis by Kirchhoff and others? They're also heavily influenced by Carl and free energy. They might have even worked with him. I sometimes, because Carl's everywhere. But with that in mind, I like the life-mind continuity thesis because it addresses a lot of things that have emerged from evolutionary psychology, biology, even like work that touches in the world of Michael Levin's world, which Carl also worked a lot with, and these ideas that there is cognition at the plant level or organism level. You can even go simpler. Like, by the way, it's hard for me, Blue, to imagine. I've been studying them, not physically, but, you know, theoretically, bacterial organisms, right? Or, you know, even like E. coli is a wonderful example of studying its behavior. It too also minimizes its variational free energy. It opens the story to other things, which is also what inspires this work that I've done very recently with Carl, that I keep teasing everyone about, but it is, I promise it will come out. But all of these things have cognition, but they are not cognitive in the way that humans are. So there's like, and I've long thought about this ever since I was, you know, studying philosophy of mind as a young undergrad. Now, of course, the thing in when I was very young was about consciousness, and consciousness is a very big world with a lot of implications that I have to be careful, because there's been philosophical theories forever. And everyone has their holes that they need to fill, and then there's flaws. And I don't want to go into like Thomas Nagel or Dennett concepts right now, but you know, I always thought, well, animals are conscious and plants are conscious. They're just not conscious in the same way. There's degrees of consciousness. And the reason I brought up the life-mind continuity thesis is that it sort of talks about like gradations or degrees of cognition and cognitive functionality. And as you go from, and I like this premise, I think it's an important premise. And since it's published work from them, it's not like I'm stealing any thunder now. It's already out there, and you guys even are nodding, so I know you know of it. You have the neurons and nervous systems, which evolved a lot later in, you know, when you look at the picture of life, right? And so what was below that? What are things that are more foundational, because other organisms might not even have nervous systems, and yet they do beautifully complex things. They elicit beautifully complex behavior. even doing photosynthesis in a plant is beautifully complex if you study the details. And it's, it's also an alien way of which they get their nutrients, right? We don't do photosynthesis, and so that it's a completely different evolved behavior. And so Michael Levin and other researchers, not just Michael, but like others, have this thing called basal cognition, which is this really, really, really low level cognitive functionality that emerges through the memory of evolution. So I agree with you, Blue. You can't completely ignore the role of evolution. In fact, it's another piece of the puzzle that you sort of have to somehow account for. And that's where the life-mind continuity thesis goes in the opposite direction. It says we have high-level cognition, our complex minds and brains. We also have simple minds and brains. And it's not like all of a sudden there's this hard, discrete flip switch where you say, all of a sudden there's a brain and then there's not a brain. It's like, no, plants do have a brain, just not the brain in which we have a brain, right? And it's not a nervous system. It's, these evolved biological constructs that, have emerged from their primordial biochemical soup of evolution to then allow them to, for example, manipulate their structure in response to the weather and rotate and move towards the light, right, to better conduct photosynthesis, and their growth mechanisms. And so their very simple behavior, obviously the plant's not going to get up and walk and figure out, oh, I want to attack this other plant, right? That's more high level behavior, although we can come up with really cool science fictions about it. But, that level of behavior is cognitive. It's just basal cognitive. And so that gives you what's called a simple mind, or even just a mind in a different part of the spectrum. And so how do we account for that? I have some thoughts, and I don't want to steal that thunder, but there's also the role of evolution. They talk about evolution in the life-mind continuity thesis and how you actually can't get even the complex minds to emerge without a memory that is evolutionary, right? So that's where you have an aggregate. And so that leads you, and the engineer in me gets a little anxious about this premise, but not because it's not the right path. It's rather my ability to contribute properly to it, because there's only so much you can do, which is, well, now you do have to think in collectives, right? You can't just model the individual anymore. You do have to have many individuals, and you need a population to then induce some type of evolutionary process, because you need what Kirchhoff and they say in the life-mind continuity thesis is a selection history. You need the selection history. It can be through the evolutionary process. Maybe there's other ways to do it that they didn't say specifically. It's just what biology does. And that's what gives you this emergent behavior, right, to create, for example, the plant cognition that we observe. And of course, the very long chain that gave rise to the evolution of, apes and primates, and then the humans from that. And so you have that selection history. So that means we need to model populations in, the processes of which they evolve. The reason I said the engineer in me gets anxious is it's extremely, my world, complex to computationally simulate just even one agent. So, and when I do evolution, and I've done neuroevolution, you usually simplify the little agents. Even the ant colony, the paper that you guys talked about, well, that was a really beautiful example of emergence and other really neat things. Those ant agents that Kant, as my colleague talked to them, they're very simple. They weren't even neural nets, let alone a common. Imagine running 1,000 common model of cognitions, and that's not even enough to do the evolution scale that we want. So that's where I say, and again, knowing that might limit what I could do, and researchers like me that go on this pathway, maybe the other solution is, okay, well, I'm just going to figure out what the inductive biases would have been that were evolved from the evolution, and I'll just skip the evolutionary phase. However, that means you could be wrong. You could have gotten the bias wrong, right? So you just say, well, I need something. So I'm going to go from there because I'm not given a supercomputer to do the simulations that I dream of doing, I have a GPU. So I'm going to build my little agent, and I'll just say, when Blue, you criticize it and you say, well, that could be the right, why is that the right bias? I'll say, oh, it's probably wrong. But, it does give me these behaviors, so if we had the right behavior, plug in my agent into your simulation framework, and I'd love to see what happens. So yeah, and I'll stop there.
So is this where sparsity then comes in, when it becomes like too computationally intensive in terms of evolving a million little tiny creatures? Or maybe this is a good time to talk about sparsity.
I mean, first of all, I see you put a link here in the chat. I didn't.
Yeah. So if you want to see a plant walk around, watch the MIT. So the MIT Media Lab has made what's it called? LON. Anyway, yeah. If you want to see the plant walk around, I've shown this before, but the plant will move. There's a little plant robot. So.
Oh, okay. I have to read about this.
Yeah, it's cool.
On the plant topic, I brought in these papers from 2017 with Friston and Calvo on predictive processing in plants, and then a paper from 89 with Silvertown and Gordon making essentially the exact same points in a broader behavioral setting. It's just like wave after wave of the realization that there are diverse intelligences over different spatial and temporal scales, and the same things that people remarked upon looking at a piece of grass cracking up through the concrete now is being instrumentally unified with the most advanced cognitive modeling that we have. And also Mike Levin's work certainly is to that point. You made a great point also about intelligence accelerating evolution, and on Mike Levin's YouTube channel there's actually a series of very good discussions to that point. Evolution trial by error and selection and pruning, and then quantum intelligence basically just teleporting you and getting to the solution without needing to traverse the entire landscape. I'll read a question.
Yeah, there's a little bit of Chris Fields there too, right? Because quantum, and I know he and Carl have been doing the quantum version of free energy and Markov blankets.
Yeah, and the course that Chris provided at the Institute over the previous months has helped put a lot of things more on a quantum footing, but that's a super exciting direction. I'll read a question from the chat. Can there be self-regulation of ensembles of noisy oracles without intelligence? If so, it would be extremely helpful for a robot mind so it can discount components that are malfunctioning.
Okay, so maybe repeat the question one more time so I make sure it's a little bit of a loaded question.
It so is, aren't they all?
Of course. Yeah, I think I need to parse it. Repeat it one more time. Make sure I get it right.
Can there be self-regulation of ensembles of noisy oracles without intelligence?
Okay. Yeah.
The without intelligence part is a little bit of a curve at the end, but can there be ensembles engaging in distributed regulation? Seems like yes, that was the sparsely connected Hopfield system that you described.
So I think the key, I wish there could be a clarification about oracle, right? Because that's usually something you ask for an answer, right? But I guess if it's just to say, oh, it's like a sensory reading, or hey, I need to query this part of myself, right? Of my morphology or my body, and I need to understand what's going on, and I say, hey, tell me, and you give me the answer. If I interpret it that way and not maybe some other interpretation, yeah, I would agree. I think our discussion has lent itself to the implication that you want ensembles. I mean, I've said this already, or assemblies, right? I've said even earlier when I was addressing some comments for Blue, and Viet's question, I believe, was part of this piece about how you implement memory. Even classical work on like auto-associative and heteroassociative memory back before even like talking about Hopfield nets. Like, oh, I have a matrix and I can update it with some Hebbian learning and outer products of vectors. And what I remember when I was studying that is that they said, well, you wouldn't use this one little matrix as the memory. You would actually stitch together an assembly of them, right? And so that's how you get this complex behavior because, you know, even in biology, all the ranging up to nervous systems, to modules and structures in the brain, they are these like self-organizing systems of parts and relationships between those parts, right? And we can interpret them as dynamical systems, and there's a lot of nice little frameworks we can apply. So the answer to that, or the general gist of that question is yes, you could build robotic systems, because I think that was the kind of the application area. And would you get things like fault tolerance, or would you get, for example, if a part of the robot's morphology or body is damaged with that, I think that that would be the right design paradigm, right? That would be an appropriate design paradigm to construct it, where you have like a distributed form of intelligence. These you might not, it might, I think the nature of the assembly might be important. For example, it would probably be semi-hierarchical or heterarchical in nature. Carl has done some really nice theoretical sketches of like Markov blankets of Markov blankets, which I will just borrow this question and that statement to address a piece of something I forgot to say to Blue in our earlier discussion of the body and the niche and the neurology or the neuronal constructs. Is I also think it's going to be important going forward to embrace, again, there are other ways to probably do this, but I do like the Markov blanket formalism because it partitions the states of the outer world, the internal states and dynamics of the system, which is very vague, but it leaves that on purpose. And then you have sensory and active states as your blanket, right? Your little Markov blankie. And I think you need to specify that. And that will give you the notion of like, okay, well, there's the theoretical body, and then we need to answer the question on how to physically instantiate that. So that was just a quick thing I had in my notes. I wanted to make sure I didn't forget to say that, because I think that's another piece of that puzzle. You need to embrace that. And then there's other arguments for it, but that's something quickly. And now that goes back to the answer to the question, is that you would want to construct, a cognitive system to manipulate the robot. Let's even leave the common model and predictive coding, because those are just other tools that you could use to construct your brain. But rather think of like the nervous system of the robot, and think of it as, I want a Markov blanket of Markov blankets, right? And Markov blankets of Markov blanket. And you can keep doing this recursive nature where now you have your little atomic unit, and that Markov blanket kind of construct, right, is your oracle, right? It has its own internal states, and that map to some physical component of the robot. I think the part is that now you are no longer just saying I abstractly model the robot in the software sense, but it actually is grounded in some physical component, hardware property, maybe a particular piece of the robot, and then you model these with these little Markov blankets, and then you have macroscopic or gradually increasing macroscopic level Markov blankets that allow you to say, well, now I have this organization, but the internal states of the higher level Markov blanket are, these other Markov blankets that have their relationships. And that goes back to my biased background in complex adaptive systems, because what do you get out of that? You get what Herbert Simon and some of the greats of our time, in the past, talk about heterarchical, partially decomposable hierarchies, right? And you build these beautiful, complicated systems of control, right? You have top-down modulation because the upper level Markov blankets are maintaining their internal states, and there's dynamics that we should probably figure out how to model that. I'm leaving the engineering side of this out because that's an interesting question of itself. And then those dynamics and those relationships and laws between those higher level units, well, they affect those lower level units, right? Because those lower level units upwardly cause the emergence or the existence of the internal states of the upper level Markov blanket, but the rules of the upper level Markov blanket downwardly cause, this is directions of causation, modulate and shape the behavior and interactions of those lower level modules. So I think the answer is yes, you could do the assembly, and the noisy oracle. Well, noise is always a part of it because, for example, physics. We always have a thermodynamic exchange with our world. There's always loss of heat. Entropy must go up. Even if we are an open system, and the entropy within us goes down, the entropy of the entire system of the niche and the agent must go up, because you can't violate the second law of thermodynamics. And I think that when you consider that you're going to have this, and you're also going to have, imperfect sensors, right? And you're going to have noisy sensors. I guess that's where the noisy oracle comes into play, because you're not always going to have a perfect reading, and you're going to have to make decisions based on that. And that's where the uncertainty part comes into play. The precision weighting mechanisms of active inference and free energy come into play. And then how do those dynamics change when, for example, a part of my system fails, right? I do think that that's a viable pathway or a design paradigm for constructing. I would don't even need to worry about the common model part, the nervous system, right, of the robot. Could we just build, that complex interaction, which is neuronal, right? But we're using sort of that hierarchy or the recursive Markov blanket formulation to design this. And you can tell I like Markov blankets because they're a nice little entity that tells you what's going on. So I don't know if that was a useful enough answer to the question, but
Yeah, it's great. I'll just note two key pieces. First, in terms of what does free energy principle and active inference offer in alternative or in addition to these other frameworks, a very clear principled articulation between the math and the theory and the implementation, which is already there in the common framework, but then to actually separate out the discussion of how to structure the Markov blankets and generative models from the micro implementational message passing on factor graphs and these features that can improve the componentry as a capacity building work, while blueprinting can be blueprinting rather than kind of needing to build the blueprint on the ground, which is always going to end up with like an overly bespoke setting. And then also, like, even when we are seemingly talking about a single mind, whatever an individual would be, we are really always talking about the relationship with the niche, the multiple agents, similar and different types, and the whole life cycle. And then you said that kind of like made you nervous or something as an engineer, because it's like when you want to think about engineering the car, not a car engineer, but one account would be to focus on the car on the freeway driving and everything working. But then actually the real systems engineering of the car is the supply chain on through the recycling and all the different ways that it can interface with things that are outside of the control. And so to just build a cognitive model that is like in silico or just has this kind of like inward perfect gaze, it may be an interesting project. But then to engage with the messiness of the world, that's where we again go back to biology. Look at how it's done and then try to accelerate or complement it.
Yeah. I mean, we can learn a lot from biology. So I think you said it well.
We could look a little bit to a paper. One of the maybe first. Blue, you focused on the first paper, or how about just what do you see in Figure 2, Alex? How would you describe Figure 2, or if there's another figure from this first paper that you want to describe, but just whichever one you feel like is the best graphical abstract, just describe how you see it.
I like Figure 2. There's a couple other nice diagrams in the paper. I'm not sure. So I think this one is a nice diagram. I saw you guys go through this. I think everyone should watch 0.0 because I think you guys did a nice job at least dissecting parts of it and summarizing the main takeaways. This is just showing you, this is now very fine grained. Our discussion, I don't know if that was the intent or maybe that's a good thing. I don't know how the podcast likes to keep things constrained, but we sort of went really high level and then philosophical, mathematically conceptual. And then, like you said, we haven't really talked about the papers, but I would say this paper in general is sort of like, okay, given that discussion, now you're back to being the engineer and saying, okay, where do I start? What's my Lego blocks? If you play with Legos or little toys and put things together to build a tower, I call this a Lego block, right? This is a computational unit. Now, you could still go further, as you guys also did look at another paper called Spiking Predictive Coding. I guess we'll save that one for next session. Which is like the same thing. It's just really, really intricate. And that would be what you'd put on neuromorphic chips. So this is like, okay, I want to build a little circuit of neurons and I want them to relate to each other. And that's what like figure A1 is trying to tell you. It says that would be sort of like your network in what's called prediction mode. And the idea is that like the little two dots, the gray dots, actually in general are what are called state nodes, or just the neuronal units. And the reason I call them state nodes is this is very different than deep learning, or at least most of deep learning, where these units always exist. And that's kind of this goes back to maybe the earlier part of our discussion. This paper is what I would call mechanistic predictive coding, right? It's saying, I'm not just telling you the principles of, error, and I bounce it around and I somehow form impressions. It's like, okay, how do I build this? And what would a neuronal model, something actually in your brain, maybe a little group of like 6 neurons, how would they be related to each other? Or, maybe you're looking at it a little more abstractly, but this is supposed to describe cortical structure specifically, but I like to think that this paradigm repeats itself and almost everywhere in the brain. There might be other ways of doing things. So in figure A1, the little 2 dots, the 2 gray circles in Z2, those are just like, okay, I have 2 neurons. So I have little regions, and those are layer 2. Then there's these other 2 gray circles in 1 called Z1. Those are another set of state neurons. And then we have another set of neurons, Z0, and that's at the bottom. So those are the actual physical neurons, and they exist all the time. And what I mean by that is that we simulate their dynamics. This is why I keep saying neural dynamics, is that they're emulated through like an ordinary differential equation, right? So you have maybe an initial condition, which is just a number that you put inside each one. So this model in this paper still has some biological constraints that, you're modeling roughly firing rates, if you want to say that. So these are like rate-coded neurons. My spiking implementation and my generalization of predictive coding tries to say, well, maybe I'm not interested in modeling spike rates. I want to model the spike trains. And this is a stepping stone to that. You actually understanding this and understanding those ordinary differential equations that govern Z of L, which is like Z2, Z1, Z0, you kind of just modify them a little bit and you outpop spike trains, which is like really cool. And I have slides that mention this a little bit, but maybe I'll use them next time since we're going over. I'll just play off you guys and the material you have here. And so Z2 and A1 is predicting Z1. And what do I mean by that? Well, Z2, I just told you, has numbers inside each of those gray circles, right? It has, at a particular snapshot in time, they have a firing rate, right? And it's just represented by a number, a scalar, and they emit a prediction using those black diamond arrows that are like kind of connecting to E1. We'll talk about E1 in a minute, but those little black diamond arrows, and I have, like terminology for excitatory and inhibitory neurons, just to tell you, when do you subtract and when do you add? But let's just forget about the math, because if we get in the math, that takes a while, and I've found confuses people, especially on these types of presentations. So just imagine those scalar values inside of Z2 are being transmitted along those black diamond arrows down to Z bar of 1. That's what that little bar, I think you can kind of see it in your visual. And that's the mean of a Gaussian distribution, because what the model that we're sort of constructing is we're saying every local set of neurons they are driving, like a car, the car of a Gaussian, multivariate Gaussian distribution. And so I embrace more of a, let's say, a Fristonian kind of view, which is that we're going to learn, in this case, somewhat of a hierarchical Gaussian model. And so Z2 makes a prediction of the mean, and that's what Z bar 1 is. In the paper, and you can see it in this diagram, but it's not like super clear, there's also a precision matrix or a covariance matrix, because a multivariate Gaussian is defined by a vector mean, and then a square symmetric matrix for covariance, parameters. And it's kind of like it lies off to the side. It's like lateral connections, really. And they are what those weird little open diamond connections in E1 are. That's the precision weights, if you will, or the covariance weights. And so between those, you multiply the mean by the precision weights, which is like a lateral competition, not even competition, it's more like a lateral pressure. And then you're done. You've made a prediction from Z2 to Z1. Z1, right, I told you has numbers inside of it, right? Because again, these neural dynamics exist at every snapshot in time. So E1 is what is known in mechanistic predictive coding as the error neurons. And we're making other biological simplifications. We could discuss them later if there's criticisms, but E1 says, okay, I also have two little diamonds, these orange diamonds, and I need two of them, right? Because Z2 has to predict Z1, which has two nodes, so it needs to have a dimensionality of 2. And I need one error neuron to compare each dimension. So there's a mapping of 1-to-1. There's a biological criticism of that, but for computational purposes, it's good. So we're going to go with it. And Z1, each dimension is compared to each dimension in Z bar 1. And we can emulate this very simply as in the paper. You can take derivatives of a free energy functional, but at the end of the day, you do all the math and it comes out to be a subtraction. Z1 minus Z bar 1. That's it. So that's called a mismatch signal. And that's sort of emulating in a very, very simple way, what's known as like the superficial pyramidal cells in your brain, which sometimes are argued to do like these mismatch computations. That's kind of one interpretation of them. And the idea, make sure that I actually wrote that down, make sure I didn't get that flipped. Yeah, no, I'm right. Yeah. The superficial. And then the state neurons are what are called deep excitatory pyramidal cells. So these are, you could almost argue I'm using a lot of pyramidal cells, but they're just neuronal units. That's just the biointerpretation. And that's pretty much it. So E1 compares Z bar 1 to Z1. And now you just repeat, right? So Z1 would be guessing the activity of Z0, which means it emulates Z bar of 0, which is the mean of the Gaussian of the layer below. And you'll have a precision matrix, you'll have a set of error neurons, but the calculation just repeats. And that's pretty much it. You have now a canonical predictive coding circuit. The interesting piece of this is very similar to like Regis-Rau's model, except it's not applied to image patches. It's just applied to sort of the vector space directly. That's what parenthesis 1 is. It's like the prediction mode. And then A2 says, okay, you made those predictions. By the way, Z2 predicting Z1 is made in parallel, which is the beautiful property that I want to emphasize right now, to Z1 predicting Z0. By the way, Z0 in this case, you would clamp those numbers to a data point. So for example, like I do in this paper, and I know you and Blue talked about it last time, pixels of an image, right? And maybe, by the way, you can change the distribution. I will add a quick caveat that the bottom layer is actually a multivariate Bernoulli distribution because I'm modeling binary pixels, but it doesn't really matter. Just pretend everything's Gaussian because it's easy to visualize for the audience. And so that's prediction mode. Those things happen in parallel. Notice that the prediction Z0 bar does not depend on anything except Z1. So for free, you get something that's already brain-like, which is a kind of answering a question I know you and Blue had about like, what do I get from this, right? What do I get? It's kind of like, what does predictive coding bring to the table? You get layer-wise parallelism for free. And that's a really nice property because if you can, emulate that, you have multiple GPUs or CPUs, you have a performance cluster, you could now actually do literal parallelism, whereas deep learning, you have to kind of like run a forward propagation pass. Everything is locked into sequence. This is parallel. Now, the problem with that is now you have to do message passing, which I know you guys are familiar with it, so I don't need to maybe go into so much detail, but that's what 2 is. It tells you how to take the messages at E1 and E0, which are error messages, right? They tell you how far off was the prediction made to the thing I wanted to look at. And then I backwards transmit that information along a different set of synapses, which is sort of what makes neural generative coding a little bit unique. We talk about this in my survey as well, compared to Rajesh Rao's model and even Carl's older models, which are essentially you would just take the transpose of the weight matrix for forward prediction. But that's not biological because we don't reuse synapses. There is no evidence of the weight transport problem, which is I go back along the weights that I transmitted forward. The brain is really recurrent. And so I embrace that. And so you have a different set of synapses. You can call them feedback if you want, but I call them error synapses. It doesn't matter. And that's what those little dashed open circle lines are doing, is they are taking the little diamonds, the orange diamond values, and they are backwards transmitting them to a particular layer. And it's usually back to the state neurons that made the original prediction. And then the last piece of the puzzle, if you just want to understand what are those dashed solid diamond ones? Well, those aren't actually synapses. They could be. They are just basically, let me take the error message and let me subtract it. And this is how you get top-down pressure, because you need to have bottom-up, top-down pressures at every layer of neurons. And so this is where that message passing happens, that one step right now, I've only shown you one step, Z1's dynamics are going to be perturbed by the message that was passed from the layer below. So in this case for Z1, it's the message from E0. And then the prediction or the reverse of the prediction of layer Z2, which is the minus E1. And that's what I have in the equations in the paper. And I could show some slides that walk you through these steps if you want, maybe next time. But the idea is that happens at Z1. By the way, all the layers of neurons do this, as long as they're not clamped to data, because if you clamp them, that means you fix them to a set of values that you're saying, well, I know what the data is. I don't need to infer it, so I'm going to put it here. So that's Z0 in this case would always be pixels of an image. Maybe they change with time, but let's keep it static. And then all you do is you repeat step 1 and step 2 multiple times, right, until you reach a steady state, which is one thing you could do, which is how many times do you repeat that? Well, you reach equilibrium, or you just bound it and you say, I'm going to run this for, like I do in the paper, a number K, 10 steps, right? And what is this doing is it's changing the values inside of Z1 and Z2 only. Notice I've said nothing about synapses. The synapses are just whatever numbers they are. The synaptic strengths are fixed at this point. So let's say I reach a steady state, or I do this for like K times. Then you make an update to all the synapses. So the solid diamond arrows, which were the generative weights, and the dashed open circle synapses, those are put inside matrices, and you just calculate their updates with Hebbian learning, right? It's really easy. I have statistics. Paper shows you those rules. It's just a matter of product. What is this doing? Well, you probably are familiar with like dynamic expectation maximization from none other than Carl, right? And generalized filtering. It's a form of that. It's just a biological manifestation of dynamic EM in this specific context. When you do things at the spiking level, you don't need to wait so long to do synaptic plasticity updates. I do those online. That means every step in time, synapses change, and you write out their ordinary differential equation. We can save that for, I think that is actually supposed to be for next time. So we can dive into that fun pile of dynamics later. And that's pretty much it. I mean, the little diagram B is just trying to show you, oh, what do the cells look like? So if I just zoom in on like one single state node and one single error neuron cell, you're looking at scalars, right? And I'm just saying, well, this is how they wire together. And then so that's just a zoom in if you want, if you will, if you don't like matrices, because engineers, we love vectors and matrices and vectorizing because then you can run them on a GPU. But the old-fashioned way in the 80s was scalars. And then on the right, we have diagram C, and that's actually showing you all four models that we investigated in that journal article. And it's cool because this paper's long, by the way. So it's funny. I admire you guys for doing 4 of my papers, and on top of them, they weren't short little guys either. This paper has a very long appendix. I don't know if you found the supplementary material. That was the reviewers. They had us do a lot of extra things. The appendix actually tells you a lot. And among the things that it does is it emphasizes something that I think the message kind of got a little tiny bit muted in the main article, but that's just how nature is. It wants you to sort of say, give me the main thing, show me the results, all the beautiful math, box it up in this nice little corner. And if people really care, they'll look at it. And so the diagram to the right emphasizes something that in the appendix talks about a naming convention. So neural generative coding isn't just predictive coding. It's like a computational framework that tries to unify as much of predictive coding as I felt that I could in the paper. And so that's why the model has underneath there GNCNT1. In the appendix, there's like a section that tells you how to interpret why do I use the word GNCN? What is T1? It means type 1. T2 means type 2. And those refer to the error synapses, because you'll see Rajesh Rao's name in the model there at the bottom, and that's to pay homage because I'm a big buff for historical research, and I like to pay credit, whereas a lot of people don't, to old work because we stand on the shoulders of giants. And so, as I told you, I read a lot of Rao's work. That model's named after him because it is effectively like the fully connected version of his patch model in his classical Nature paper. And that is a neural generative coding network under specific assumptions. And so, like any mathematician, you just say, oh, I recover this older model because it's a subset of my theory. And then the second model, usually it's a little bit similar to Rajesh Rao's. It's essentially Carl's model from either 2008 or 2010. The reviewers wanted us to implement that. And it's not a model that many people, I hate to say, implement besides Carl. So I had to do that. And it was fun. And basically, it's just a large piece of it is making sure you get those precision matrices right, because he introduces that in one of his like graphical model papers. And so that's why it's named after him. That pays homage to his classical work. And then the 2 to the right are the new models. And that's the ones that, like, for example, have separate feedback synapses, which is not something that older models directly addressed. Carl has mentioned them, but at least the mathematics or the models that of those papers did not concretely tell you how to implement them, let alone how to learn them. So all of my models, all my synapses are learned with like Hebbian-like plasticity. And then the last model, the farthest one to the right, the reason I'm spending time on these is because those are the core models we looked at in the paper. The one to the far right just says, oh, well, because NGC is such a broad framework, you are not committed to a hierarchical model. You could build a heterarchical model or a weird model that has skip connections, right? And so that's why you see this like weird arrow going from the very, very top layer all the way down to the bottom. And so the math in the paper shows you, oh, I can turn off with these little gating variables, these weird kind of skip connections that violate the hierarchy, but you can still learn them in Hebbian ways. So the efficiency is all there. It turns out that model actually worked the best. And so you guys actually showed in point 0 the data samples, and those are what I used. I use the final model, the GNCN PDH. That's like a little compression, because when you use a naming convention, the names get really long to a certain point. So you're just like, well, I'm not going to say GNCN T2 L sigma, which refers to the lateral connections and the and the precision weights, and PDH. I'll just call it PDH, right? And you can just say that to your friends, and it's quick and rolls off the tongue. So that's a little weird naming thing I did. And so the nice thing about these models is they do show you pretty much all the mechanics, at least visually. And then the other piece to this puzzle is you'll notice those gray circles back in figure A also have synapses that I didn't really address. Those are lateral synapses at the state node level, which is also something that, classical work like Rao's and Friston's models and others don't really use. This is something we introduced, which encourages, like, what I would argue, extreme sparsity. And the motivation for that, because I know Blue had a question or just wanted to chat a little bit about sparsity, so maybe this is a way I'll sneak it in, is that Rao, for example, introduced sparsity by imposing a quadratic Laplacian prior, which just is basically a pointy distribution over the neural firing rates that just say, I want some of these neurons to go to 0 and other ones to be high, and I want, as many of them to be 0 as possible. And that's a useful way to do sparsity. It actually comes from Bruno Hausen and sparse coding work, and I cite Bruno. I've met Bruno Hausen too. He's a cool guy. You can get these activities to be really, really, really sparse. So most of them are 0, because 0, why do we care about 0? Not just from a biological point of view. Hardware loves 0. 0 means I don't compute it. So if I don't have to compute it, I don't use any hardware resources for it. I can ignore it. It's those numbers that aren't 0 that are annoying for a computer. And so instead of doing a Laplacian prior, which I did investigate in this paper, and I think I even have the dynamics in there as well. It's like one of the equations. And to be faithful to Rao, Rajesh, I had to put that in there. But the lateral synaptic connections at the state nodes, what they do is what we did in this one is we introduced fixed weights, because that's the easiest thing to do. You don't have to learn them. Later on, I've learned them. That's like some future work. And what these lateral synapses do is they have it's like a matrix, and they are shaped to be a square. And they are like, let's say, the dimensionality of a layer. So in the top layer, it'd be 2 cross 2. Along the main diagonal are a set of positive numbers, or maybe negative numbers. You have to make sure that the middle diagonal is excitatory, and it's called self-excitatory, which means if a single neuron fires at a step in time, its new firing rate is going to be amplified by its own firing rate. So that's called self-excitatory or self-excitation. And the off diagonals, so the lower and upper right triangle of this lateral matrix that I'm talking to you about, that has to be the opposite sign. So I would believe it would be negative unless you wrote the negative sign in the ODE, then it changes. And those are negative numbers. And the idea is that those put a downward pressure and says this neuron, let's say in this one element of the column, will laterally inhibit other neurons in that layer. And the cool part, and again, it's in the super long appendix of that paper, you can find it. That matrix, even though I fix it, because you could try to learn it with like Hebbian learning, and I later like investigated that. What you might say, okay, I'll put some random numbers in that matrix, but wait a minute, do I really want every neuron in the main diagonal to inhibit all the other neurons? The answer is probably not. You could. That is a type of pattern. What I did is I initialize a masking matrix. And in that matrix, without going into the details of that, because there's a little bit of an algorithm, it just basically says little groups of neurons inhibit each other and no one else. And so you basically turn off things in that matrix, you fix it with a mask, and now you get group sparsity. And so the long story short, with all of that cool description, is that you get K winner take all type lateral competition, but it's biologically implemented. So I'm not like using an activation function. And as you go through the dynamics of this model, this matrix, what it'll do is it'll emphasize neurons that are really important for the object that you're processing, and it will shut up all the other neurons that aren't relevant, right? And so this is to answer a question, I believe it was Blue and you, Daniel, were discussing last week about the results that we had in this paper, because it's not shown here in this diagram, but the idea is that we also got really good classification performance. This model has no label, right? So we trained like a little probe or whatever on the topmost layer, and we also showed some TS&E plots. And the reason I think that the model works as well as it does for something it wasn't trained to do, which is discrete categorization of object categories, like different numbers, like the digit 0 is the 0 category, is because of that sparsity. And we did measure the sparsity levels, and they were really, really, really tiny. The proportion of neurons that were active as you go through these dynamics, especially as it learned, is it said, oh, I don't need a lot of neurons to represent 0. So it's sort of like extracted out little subnetworks that specialize to these templates, right? So we didn't exactly probe that hypothesis, but that's what I speculate is going on. And it's also very easy. You can justify it from the past. You can say sparsity is a really important way to do memory retrieval. It's a beautiful way to fight catastrophic forgetting, which is another piece of my work that tries to look at that. And the idea is that you're going to get non-overlapping representations, right? So, if we only have a few neurons in a sparse distributed memory, semantically, if these units activate, they're probably related to roughly the same concept. And you'll learn, as long as you have big enough layers, of course, this is the thing where you do need like brain level stuff, you need lots of neurons, you'll find that they don't crosstalk with each other. They don't fight each other so much. So knowledge for 0 doesn't fight with the knowledge of 2. And so you'll have this nice, beautiful separation. And I think it makes things like classification a little bit easier. It's really nice for fighting forgetting because you'll remember things a lot more until eventually you run out of capacity and then you just need more neurons. And it's also energy efficient. So the big argument is if everything is 0, except for like a few neurons firing, that's a perfect candidate for neuromorphic computing. And then if we can make them spike, which is what the other paper you guys reviewed tried to do, then we solve all of those weird things because you should only be communicating with bits. You shouldn't be communicating with rate-coded continuous values, which are clean, but they're not good for hardware like a neuromorphic chip or a memristor. So that's kind of the general gist of it. And I think that's where you get this beautiful benefit of sparsity and you see this nice interaction and you're learning a generative model. And of course, that paper actually synthesizes the models. We look at what samples are produced. And I could keep going on, but hopefully that was useful and made sense. I see Blue is gone, so maybe I got boring here.
That was great and a lot.
Yeah, it was a lot.
What are you
Did it
looking
make
for?
sense?
It
Even a
helped
little?
me. It helped me even after reading all the papers multiple times. Hearing this explanation still really did help. I hope it's helpful for other people too. There's an enormous amount of condensation, but you really are laying it out like an engineer. How do we build the 3-story building? What's the wiring diagram of each floor? And then you're clearly striking a fine balance with how much of the mathematics to visually convey versus explore here. And that's why there's appendices. That's why there's sequences of papers. What are you looking forward to in .2? Or just as we kind of close out?
Yeah, I don't know if we went too long. I'm sorry if
it's fine.
I've much. Well, I mean, I'm looking forward to continuing some of this discussion. I think we didn't really even touch on the convolutional one, which is really, you could even argue, is more of a core. to use Carl's terms, you could think of it as the convolutional neural coding is a corollary to the neural generative coding framework, because it just says, wait a minute, how do I do image processing in an efficient way? Let's do deconvolution or convolution. That could be something we briefly touch on next time. I'm looking forward to the spiking stuff because I really, really love spiking neuronal cells. And I don't think he was able to make it, but one of my students works with me on spike timing and synaptic plasticity that's driven through solely spikes. So I have a particular soft spot for that. And I think the future predictive coding, at least where I'm trying to lead the crowd, is to do things at the spike level, because neuromorphic computing offers beautiful energy efficiency. We could do edge computing. So I'm looking forward to some of that chat. I also love, we sort of borrowed a big chunk of what I think you wanted, Daniel, us to do with the cognitive architecture, because we kind of brought all that today. I know Blue's very interested in that, so we sort of front loaded with a lot of that. So I was going to say I'm looking forward to that, but I mean, I'm always looking forward to chatting more. I think we front loaded it, so maybe we could address more the predictive coding pieces. However, I do have slides that I'll probably share if you want me to, and maybe talk about other aspects of the cognitive architecture that aren't just the CogNGen, but rather like, oh, I'll show you something I did in robotics. In a paper at ICRA this year, I could show you some things about how you can make predictive coding do something a little bit more concretely active inference without obscuring it with the common model. Because I think the common model is like, you get kind of lost, not you, but the audience in general might say, oh, all these continents of mind, and how do they relate? Well, wait, where's the active inference? And I talk about there, it's in there. I think sometimes it's good to say, let me throw away all that for just a minute, because memory can kind of cloud it. Let's just look at epistemic foraging and prior preference, and maybe do something simple like have a robot arm manipulate an object. And I could talk about that. And also just chatting more about like the future of this. I think that this is, I think what I am trying to represent, and actually with a lot of discussion with Carl, I think I've narrowed down what I bring to the table to the fields of cognitive science, computational neuroscience, and machine learning, which is the triad that my lab represents, is this thing called biomimetic intelligence. And I think that we need to understand the neurophysiology, the biology of things, and also understand the physics of things, and understand how the niche and the body and the neuronal constructs all interplay together to then build technological artifacts that do things like robotics in an energy efficient way. And I think this is that path. This is one possible pathway to AGI. I think it's the path, but I'm obviously could be clearly wrong. We all don't know until we get there, and we have perfect hindsight. But I think that could be a fun little bit of discussion, because I know you guys were interested in knowing about the future work that my team has been trying to do, as well as the history of those papers, which I didn't even get to talk about. I know Blue had said something she was interested to know what was the order of these papers, and I had this in my notes. So we can save those for the next session if you guys want to talk about them, or other questions. I'm open to anything, really.
Yeah, this was huge. It really is a tour de force of cognitive science and engineering. So I hope that people enjoyed it. Looking forward to talking next week. If you're watching .1 now and you want to join next week, this may be possible. And thanks again. See you.
And thank you for having me.
We appreciate it. See you. Bye.